Thank you very much. My name is Freya. I'm a researcher with nanoFCM as part of our analysis service, and I'm going to talk to you about our nanoflow cytometry platform. I'll start a little bit about the technology. So the NANOAnalyzer, as we call it, our nanoflow cytometer, is based on traditional flow cytometry principles, except this is specialized down to nanoparticle sizing. And we accomplish this through a variety of specific parameters in the instrument. The first one is a slow particle flow rate. The flow rate of the instrument is nanoliters per minute, and what this does, because we want to achieve as much resolution as possible, as much detection as possible, slow flow rate extends the particle dwell time in the laser beam. Combined with the use of single photon counting APDs, our SPCMs as we call them, single photon counting model. These are highly sensitive detectors that allow us to detect very low or very dim particles that are in the fluorescence channels we use. We also have a very fine sample core stream where the inner diameter of the capillary that feeds the instrument is 1.4 microns in size. This allows us to pass nanoparticles through the laser as much time in front of the laser as possible and resolve them one by one. This is an animation of what a sample goes through in the instrument. So we first start by loading the sample with less than 1 microliter being consumed. As it passes through the instrument, in our base model, it passes through 2 collinear lasers, a blue laser and a red laser. The blue laser The blue laser is paired with 2 detectors, one in side scatter, which allows us to measure size and concentration, and a green detector, which allows us to measure fluorescence in the green channel. A red laser is paired with a red detector to allow us to detect red fluorescent events. And this is a depiction of what the output looks like. Specifically, I want to draw your attention to the event burst traces. This is how we identify a particle as distinguished from the background. So you see on the top, we have a blue event burst trace, and on the bottom, we have a green in the FITC event burst trace. We take data first from side scatter, where we look at the intensity and whether there is an event as distinguished as a vertical line above the threshold. Any event with a vertical line above the threshold is determined as a particle. And the threshold for this varies based on the composition of your particle. For biological particles, we say the detection is good down to 45 nanometers in size, with our ideal size range being up to 1000 nanometers. This information is then paired with data from fluorescence. So you can see in the green box, we have an event in side scatter, which is a particle. That is paired to an event in FITC, which is what we determine to be a FITC positive particle, compared with the events in the right, where we have an event in side scatter, but not in FITC, where this is a FITC negative particle. Because we detect particles on a single particle level, we can then graph each individual particle on a dot plot to see which particles are FITC positive and which are FITC negative, which we can then gate. Our base model, as I say, has 3 detectors, 1 for side scatter and 2 for fluorescence. Side scatter is responsible for the detection of size of the particle and size and concentration, which we can achieve through the use of side scatter intensity. Whereas fluorescence allows us to label your particle with any antibody or stain that is fluorescence in the channels that our detectors provide for. And in the past, this has included proteins on the surface of your particles, such as tetraspanins, different signaling molecules, or targeting peptides. We can also look at cargo loading. This is commonly nucleic acids for things like lipid nanoparticles, or even loaded proteins in the case of EVs. We can also look at lipids themselves. So we can distinguish selectively the lipid or the lipidic membrane content of your samples. The instrument has very high sensitivity and very good resolution. Our sensitivity, as we say, for biological nanoparticles can go down to 45 nanometers. However, based on the composition, we can go down to see and resolve 24 nanometers for silica, and down to 7 nanometers for gold particles. Our resolution matches up very well with cryotransmission electron microscopy. As we can see, we can clearly distinguish populations of silica beads between 40 and 50 nanometers. And this sensitivity and resolution also matches with our fluorescence, where in ideal circumstances we can distinguish single molecules of PE fluorophores, and we can resolve population of beads, as we can see here, from 61 equivalent reference fluorophores and 131 ERF. This has been used for a wide variety of applications so far. Most popularly, we work with a lot of extracellular vesicle samples and lipid nanoparticles or other non-viral nucleic acid delivery systems. We also have some work with lentiviruses, all of which I'll discuss soon. I'll start with extracellular vesicles purely because this is what forms the bulk of our applications so far and the biggest portion of our experience. So the benefit of the instrument is we can look at size and concentration completely unlabeled. So if you don't wish to label your particles for any reason, we can still give you full size, concentration, and size distribution. However, with the addition of labels, we can then look at surface markers, whether that's tetraspanins or other interesting biomarkers that are relevant to your work. As I mentioned, we can look at the lipid bilayer, and we've cited a paper here from our own team where we can selectively stain lipid bilayer and distinguish it from common contaminants in extracellular vesicle samples such as VLDLs, LDLs, and VLPs. We can also look at internal cargo through permeabilization fixation, whether that's naturally or synthetically loaded for therapeutic purposes. This is some work we've done on surface protein characterization. So this is an EV population where we have labeled it with CD9 AF488 antibodies. We see on the left we have a population of 80.5% of CD9 positivity in our sample. And because we can then gate this and we can determine not only the fraction of EVs that are fluorescent for this label, we can then look at size distribution for each subpopulation as well as concentration. When we tested this for CD63, we found a positivity of 70.2. And this is to highlight that we can also detect things in the red channel, such as fluorophore with AF647. Some advanced analysis we can do with surface quantification, and this is true for any particle, not just EVs, but we have a set of standards where this is a population of silica particles, or silica standards, with 5 populations of beads, each containing relative brightness equivalent to 61 particles of, well, 61 fluorophores of AF488 and going up to 1,438 fluorophores. What we can then do is we can plot the intensity of each bead with the number of fluorophores to arrive at this equation. And we can use this equation to calculate the equivalent number of CD9 molecules on the surface of each particle at a single particle level. You can see here we've done it in 2 channels, again, AF488 and AF647, with an equivalent reference value of 33 to 34 CD9 molecules per particle. And for CD63, we found a median copy number of 17.5. Looking at intraluminal loading, we did some work with Vesigen Therapeutics, where they provided us with these modified microvesicles that contain a restin domain containing protein 1. They are using this model because they are recruiting proteins to the intraluminal space for the purpose of delivering RNA, proteins, gene editing complexes. And to interrogate this, they set up a system where to the interior of the lumen of the EVs, they anchored the ARRDC1 protein to an EGFP molecule, which is detectable on our green channel, and a targetable peptide spot. We used this to verify some labeling. So first we started with GFP only unlabeled control, and we found good detection of the GFP molecule. We then fixed and permeabilized the EVs and labeled with a spot-specific nanobody in the red channel, and we found a staining efficiency of 87%, and we can identify this by the dual positivity population. This is applicable for a range of different EV purposes, whether you're only interested in physical parameters such as size distribution and concentration. But with the addition of biomarkers, we can look at protein marker expression for interesting particles or interesting expressed proteins. We can look at loading for therapeutic devices, and this can be relevant for any part of EV production. Talking about LNPs, you will find that like EVs, we can do size and concentration of lipid nanoparticles, also unlabeled. We can look at surface markers for targeting peptides, which is quite a popular area of expertise or exploration in lipid nanoparticles currently. We can also do advanced characterization with these for the fluorophores of AF488 and AF647. We can look at internal cargo, which popularity is RNA or other nucleic acids. We've done some work with a wide variety of cargo for nucleic acids and DNA species. We can also look at drug products. We can also look at other materials. So because we resolve everything on a single particle level, you'll find I'll keep going on about this. This is really the beautiful part of this instrument. That we can look at free RNA down to a length of 1,000 nucleotides currently. And we can also distinguish empty LNPs to really interrogate the preparation of LNPs. I'm going to talk a little bit about the mRNA labeling quantification, because this is how we do the advanced characterization and advanced quantification of mRNA loading. So our standard protocol involves staining membrane permeable nucleic acid dyes on the LNPs, and this saturates any nucleic acid species, whether that's loaded in an LNP or free in the population. Using our nanoflow cytometer, the NANOAnalyzer, and taking advantage of the 2 lasers and 3 detectors, we can arrive at some advanced data analysis parameters, including LNP loading ratio, so which LNPs are loaded with nucleic acids, the exact mRNA copy number per particle, as well as RNA encapsulation efficiency, and this measures up very well with ribogreen. So we start here by validating the labeling. We stained our unloaded control with some example LNPs and found a false positivity rate of 0.6%, which is nice and low. We can then distinguish mRNA loading, which in this instance is 95.7%, which reflects the amount of LNPs that are loaded with mRNA. Where the advanced quantification comes in is distinguishing the different populations. So we have population 1, which is loaded LNPs in the green, population 2, which is empty LNPs or unloaded, it's not associated with Cyto9, our label, free mRNA, which is positive in the fluorescence channel, but not in side scatter, so it's anything that falls below the side scatter limit. Using the brightness of the free mRNA, we can calculate the relative brightness of each particle and arrive at an approximated copy number. In this instance, it's 3.2 copies of mRNA per LNP, with an encapsulation efficiency of 98.33%. What we also did is, because all of this data is correlated with size and on a single particle level, we did some work with precision nanosystems, which has since been acquired by Cytiva. LNP1 we see has a loading ratio of around 90%. LNP2 also has a loading ratio of around 90%. However, you can see based on this dot plot that the expression and the loading has different distributions. You can see in LNP1, a lot of events are above this line, this dotted line. However, in LNP2, most events are below this dotted line. And this is reflected in median copy number, where LNP1 has a median copy number of 7 copies per LNP, and LNP2 has a median copy number of around 2. You might think based on this alone that LNP1 is the preferred formulation for nucleic acid delivery. However, we correlated this with each particle and found that LNP1, although it has a higher median loading, it has a wider distribution of loading. And LNP2, although it has a lower median, it has a much more narrow distribution and much more reliable dosing. So in this instance, Precision Nanosystems identified LNP2 as the preferred formulation for giving a reliable and consistent dose. This reflects in lentiviruses as well in terms of viral delivery. So we've done some work again with size and concentration, unlabeled and labeled as well. We can look at envelope proteins such as VSVG. We can look at capsid proteins such as P24 and the genome, whether natural or recombinant, using much the same strategies that I have just outlined in extracellular vesicle work and LNP work. First, we start with envelope permeabilization. This is a slightly modified protocol based on the work we've done with interior cargo staining with EVs. This allows for labeling of P24 capsid protein. Using our next generation instrument, which has a third laser and a fourth detector, we can look at triple stained particles. In this instance for lentiviruses, we looked at surface VSVG expression in the green channel. We looked at genome expression or genome loading in the red channel with Cyto62, and we looked at P24 positivity in the far red channel. And I will talk a little more about our next generation flow cytometer after this data. So for VSVG, we found a positivity of 79.3%. We found a positivity of P24 of around 70% and a genome positivity of almost 97%. And for each of these subpopulations, we can look at size distribution to see how large each particle is for each subpopulation. The advantage of doing this simultaneously with collinear lasers is that we can look at triple positivity. So you can see here, this is a depiction of where each population would start, with P24 on the x-axis, VSVG on the y-axis, and Cyto62 or genome on the z-axis. When we look at double positivity first, we looked at the VSVG and genome positivity. We found a dual positivity of 76.1%. We can then gate on P24 positivity, where we take that dual positive population and gate on P24, and we found that 59.6% of particles are positive for all three, VSVG, genome, and P24, and this would be equivalent to a viral infectious titer. This is also applicable for a range of parts of your development, whether that's through manufacturing or quality control, looking at size, concentration, purity, and expression. And this is using our advanced or our next generation system, which includes a third laser. In the data I've just shown you, it includes a far red laser with an additional far red detector. However, there is also the option of including an orange laser, which is suitable for fluorophores like PE. It also features an automatic cleanup and carousel for loading up to 20 samples per run, just to really speed up your analysis. And this includes our features that I've talked about, which are the advanced quantification of surface molecules, as well as nucleic acid copy number and encapsulation efficiency. In summary, this is a very easy instrument to use. It is very high throughput, so each sample we can measure within 3 minutes, including cleaning steps. We can get size distribution and concentration from unlabeled particles and a whole wealth of information from fluorescence labeled particles as well. We have a number of users around the country, quite a lot of them. We have instruments in more than 30 countries on 5 continents, as well as more than 300 users and 700 plus publications and counting in high impact journals, including Nature and Journal of Extracellular Vesicles. Thank you for listening. If you have any questions or you'd like any more information, I'm happy to answer any questions, or please don't feel free to reach out and we can have a good chat. Thank you very much.